Hello, my name is Garen, and I'm going to be talking more into neural nets. So, three blue, one brown's video is pretty interesting. The cost function measures how well a neural network is performing. It quantifies the difference between the predicted output and the actual target output. Essentially, a nice, smooth cost function is desirable because it allows us to find a local minimum by taking small steps downhill, essentially reducing the cost. Artificial neurons in a neural network have continuously ranging activations. This means their outputs are not binary but can take on a range of values, which makes the cost function differentiable and smooth. Gradient descent. Gradient descent is the process of repeatedly nudging an input of a function by some multiple of the negative gradient. Essentially, it's an optimization algorithm used to minimize the cost function. The idea is to iteratively adjust the parameters, in this case the weights and biases of the network to reduce the cost. At each step, the parameters are updated by moving in the direction of the negative gradient of the cost function. So negative gradient points in the direction of the steepest descent, which is the direction to move to reduce the cost. In this case, the negative gradient has two important components, which are sign and magnitude. Sign is whether the corresponding parameters should be increased or decreased, and magnitude is how much the parameter should be adjusted. Li took a deep neural network and shuffled the labels of training data before training. This means the input data was no longer associated with the correct labels. Despite this, the network was still able to achieve high training accuracy, meaning it memorized the random labels. The network achieved the same training accuracy as it would on the properly labeled data. This shows the network has enough capacity, the millions of weights, to memorize the random mappings between inputs and shuffled labels. So I think the lesson here is that neural networks are better suited to learn on structured data, but it can also learn on random data, but it'll be much slower. I think Ava Amini's exploration of neural networks' capacity to generalize or fail to generalize the new domains and regimes is fascinating. Just on how these models behave when trained on scrambled or randomized data is fascinating. So in her example, she proposed a random dice. Each image in the dataset is assigned to a random label based on the die roll, with k sides where k is the total number of possible classes in the dataset. The labels no longer correspond to the true content of the images. Say, for example, a cat is a dog now, a tree could be a car now. The neural network is trained on this scrambled dataset where the labels are essentially random. Over time, the neural network achieves close to perfect accuracy on the scrambled training data, which demonstrates the network's ability to memorize the random mappings between inputs and labels, even though the labels are meaningless. As you can see in the picture below, the original dataset wasn't getting that high of accuracy, but with the training set, they used the training set to get almost close to perfect accuracy. So Demis Hassabis, he proposed a conjecture. He said any pattern that could be generated or found in nature can be efficiently discovered and modeled by a classical learning algorithm. By doing a massive amount of pre-compute upfront to develop a good model, then use the model to efficiently explore solution space in polynomial time. He believed that if it turns out that classical systems can model certain types of quantum systems, they could potentially have a big implication for complexity theory. If you guys don't know what complexity theory is, it's a study of how order and patterns emerge from the systems that seem chaotic. They're used to model interactions between humans and environment. So his conjecture suggests that classical learning algorithms, given the sufficient pre-computation, can efficiently model any natural patterns, including potentially certain quantum systems. I think this idea has profound implications for complexity theory, quantum computing, and scientific discovery. While the conjecture is ambitious and faces challenges, it reflects the growing power of the classical AI systems and their potential to unlock new insights into the natural world. If proven true, it could reshape our understanding of computations and its limits. Thank you.